This is a continuation of Lesson 2 from Cycle 2. We were looking at average rate of change and instantaneous rate of change in the last part. Now we're just going to get a little bit deeper into it in this lesson. So we'll start with an example. A golf ball is lying in the grass and it's hit so that its initial velocity is 25 meters per second. The height h in meters of the ball after t seconds can be modeled by the function h at t equals negative 4.9t squared plus 25t. And it says use Desmos to help you determine the average rate of change in each of the intervals below. So here's the intervals here, and so this is height versus time. But height is going to be like our y value, right? And t is going to be like our x value. So output, input, and then this is going to be our slope here. So it's just a table to help us organize our thoughts is all that's going on. And we're doing average rate of change for this part. So we'll start by typing this into Desmos. And for Desmos, I will switch h to y, and I'll use x instead of t because that's what Desmos understands. So y equals negative 4.9x squared plus 25x. And as you can see, there's a nice graph of it. Although we can certainly make better use of our screen space if I adjust the x values. It only goes from about 0 on the x-axis to 5 point something, less than 6 anyway, because we're not going to go below ground. This is supposed to be a golf ball shot, so anything below the x-axis wouldn't make sense. So let's adjust. Let's go from 0 to, I don't know, let's say 0, oops, not on the y-axis. Did not mean to do that. Let me zoom out again and redo it. 0 on the x-axis to about 5 on the y-axis. That's better. And I can still play with it a bit. I mean, if I want to get it better on the screen, I could play with the y a little bit as well. Right now it's going up to 50. Maybe just have it go up as high as 40. There. That's a bit closer to what we had anyway. All right, so there's the graph. So what do we want to do? We want to find from the interval from 0 to 1 second the change in height. That's what delta h means, change in height. So we need to find out what the two heights are. At 0 seconds, that's pretty easy. That's the point 0, 0. A good way, an easy way to get the point, well, it looks like we got a point of about 1 and 20, 1 comma 20 for at 1 second. But if I want to be precise, I could add a vertical line. So I could go x equals 1. It adds the line, and then I could just touch it to find out what the point of intersection is. And I can see it's actually 20.1 is the height. So the change in height, it goes from 0, a height of 0, to a height of 20.1. So it's going up by 20.1 meters. And going from 0 to 1 seconds, it's going up by 1 second. And so the average rate of change is going to be 20.1 over 1, which is 20.1 meters per second. And I didn't write it out, but what I was doing is I was just taking the height of 20.1 meters and subtracting the height of 0. So basically doing y2 minus y1 to get this. And I was doing time of 1 second minus 0 seconds, again, x2 minus x1 to get this. And then the last column is just our rise over our run. So then I'm going to move on. I'm going to do the next one. And so I'm going to look at what happens now from 1 second to 2 seconds. So again, if I just want to see what the height is at 2 seconds, maybe let's add a second line here, x equals 2. see what that point is, and it's 30.4. So the change in height is going to be at second height 30.4 minus the height at 1 second, which was 20.1. The difference between the two is 10.3. And change in time, we're going from 1 second to 2 seconds. The interval is again 1 second. So the average rate of change is going to be 10.3 over 1 second, which is 10.3 meters per second. So already we can see the rate of change is changing. It's not constant, and so it's changing as the graph goes on. So that should make sense to us. If we were to connect a line between 0, 0 and 1 and 20.1, if we were to connect a secant there, that would be fairly steep. In fact, it would be more steep than if I was to connect a secant between 1 and 20.1 and 2 and 30.4. You can see that's less steep, that secant. So it's flattening out a bit. It's the rate of change is becoming less. Now we want to find out one more. We want to find out as we go from 1 second to 1.001 seconds. So we already know that the height at 1 second is 20.1 meters. So whatever the height at 1.001 seconds is, we can subtract 20.1 from that. And again, I can make it pretty easy on myself if I just put 1.001 in as my x value and then find the point of intersection. Now I can see the y value is 20.115. And when I subtract those out, I get 0.015. That's meters. So it's a very small change in height, but that's because it's been a very small change in time. It's been 1/1000th of a second, so no wonder, right? So again, the difference, if I subtract this from this, the difference is 0.001 seconds. And now my average rate of change is 0.015 divided by 0.001, and it turns out to equal 15 meters per second. What's the relationship between the secant and the average rate of change from the table? Well, the slope of the secant line is, if you remember, the average rate of change. All the slopes are positive in the table anyway, because the ball is going up at this point. It hasn't started coming back down due to gravity yet. Use the movable point to create a tangent line that touches the graph only at the point that corresponds to t equals 1 second. How can the values of the average rate of change in the table be used to estimate the slope of the tangent at 1 second? Well, that's basically what's actually happening. Let's answer this part first. How can the values of the average rate of change be used to estimate the slope of the tangent at t equals 1 second? That's what's really happened here in this third row of the table. We've made an interval from 1 second to 1/1000th of a second, so a very small interval. That's almost going to be the same as whatever a tangent line is. And so it's going to be a good approximation of the instantaneous rate of change. So we use a very small interval for the x values. That's how we can use it to estimate the slope. And we saw that with the difference quotient in our last lesson. A good interval is 1/1000th of a unit, whatever the units are. Sometimes people use 100th of a unit, and that's okay, but 1/1000th, I believe, is obviously more accurate. I think it's the best to go with. So as for this movable point, if we go back to Desmos, I've got an animation here that I can show you. So this point is this line, this dotted orange line. No, I think it's better when it wasn't projector mode. This dotted orange line is the tangent line. And look what happens as I drag the point around. You can see that it's steep here, and as we move along the graph, it becomes less and less steep, until we get to the vertex where it actually flattens right out. And then we start getting into, as we get over the hump here, we start getting negative slopes for our tangent lines. And I can animate it so you can see. It just keeps getting steeper and steeper in a negative way, and then it starts over again. Is the way I've got it set up here. So this is the tangent line as we move along the curve to get an idea of what the instantaneous rate of change is. So if we want to see what the instantaneous rate of change is at 1 second, then we just need to stop the animation when we are at the 1 second point. So about there. Now let me pause it. Actually, I could either drag it back like that, or I could have just typed in 1. But anyway, there it is. There's 1 second. And if you look down the bottom row where it says G at C, that's telling us what the slope is at that one, at that point. And the slope is 15.2. So our instantaneous rate of change at 1 second is 15.2 meters per second. And that compares favorably with what we calculated in our table. We came up with 15 meters per second. So not exactly the same, but close enough for sure, right? So using that teeny tiny interval gives us a good enough approximation of the instantaneous rate of change. Just again, notice how it's steeper. Earlier, you can see the line is steeper here. At 0, the instantaneous rate of change is 25 meters per second. And this is representing a golf ball, right? As gravity takes over, as soon as we start, it's launched, it starts losing its upward motion, its upward force. And so by 1 second, we saw it's down to 15 meters per second. At 2 seconds, it's dropped all the way to 5 meters per second. And then here at the very top, I'm not sure if I can get that quite right, but around here, we got a slope of close to 0 at about 2.5 seconds. Then it starts coming down, it starts picking up speed, and the instantaneous rate of change is getting greater and greater until when it hits the ground, it's back to negative 25 meters per second. You know, the same speed as it took off with, except coming back down due to gravity. What does the slope of the tangent represent in this situation? Well, we already mentioned that. It's the instantaneous rate of change. IRC, instantaneous rate of change. What would happen if you approached t equals 1 from below? That is using t equals 0.9, t equals 0.99, t equals 0.999. Okay, let's go back to, I don't know if I can go back to my previous graph. I think I have to just, let's just go for a new blank graph. All right, so what it was, so we had y equals negative 4.9x squared plus 25x. Let's make it fit again, x-axis 0 to 6. Good enough. All right, so what we want to do is we want to go back to calculating some secants again, just so we can see how as we make our intervals smaller, we're going to get more and more accuracy. So remember, when x was 1, we had a y value of 20.1. When x is, so if we come at it from below, so let's make x 0.9. Let me just zoom in on the difference between these. Then we have a y value of 18.531. So 20.1 minus 18.5. Maybe use a calculator on here. 20.1 minus 18.53, I think it was. And if I divide that by the interval was 1/10 of a second, we get an instantaneous rate of change of 15.7 meters per second. We know the correct one is 15.2. So using an interval of 1/10 of a second wasn't bad. But if we make it a smaller interval, let's say make it let's add a 9 here, now our y value is 19.95, let's say. So still 20.1, but we subtract 19.95, and we divide by 0.01, so 1/100th of a unit, and it equals 15. So that's closer to the 15.2 that we were expecting. If I do it one more time and make it 0.999, then hopefully it might get should get closer still. You know, there's limitations to what Desmos can do as well, so it might round it. I might not get exactly what I'm looking for, but we can see. So it's 20.1 minus 20.085. Actually, I can see that as also going to be 15, so we're not going to get any more accuracy, but I think that is just because Desmos has been rounding things just to 3 decimal places. And but if it carried more decimal places, then using an even smaller interval would get us even closer to 15.2. So that's the takeaway for that last part. You're going to get closer to the slope of the tangent line. Your answers will become more accurate as the interval decreases. In other words, as you get a smaller interval between the 2 points in the secant.